Good morning, students. Welcome to lecture number 14. We are beginning with chapter number 2 of Signals and Systems. So, chapter number 1, we took around 13 lectures and I had given you some assignments. I hope you people are following it and doing it. So, to start with the second chapter, the title of the second chapter being Time Domain Representation of LTI System. LTI system is nothing but linear time invariant system. You have already understood the property of the system, linear systems and time invariant systems. So combinedly we call it as LTI system, linear time invariant system. Throughout this subject, henceforth, we'll be focusing on linear time invariant systems. So let me present my screen. Welcome you for lecture 14. So we are studying about chapter 2, that is time domain representation of LTI system. The topics covered in today's session are Introduction to time domain representation and the convolution sum, a very important topic. The contents in time domain representation of LTI system chapter are goes like this. First, we will be studying about introduction to time domain representation, then convolution sum and integration or integral, convolution integral, system interconnections of LTI systems and relation with impulse response and step response, differential and difference equations, representation of LTI system, block diagram representation, that is direct form 1 and direct form 2. So these are the topics that we are covering in the chapter number 2, which is called time domain representation. So before we proceed with the actual content, let me tell you what is the meaning of time domain representation. You know, in signals and system, we have two kinds of representation. One is time domain and one more is frequency domain. So till now you people had an idea that time and frequency are one and the same. Time is inversely proportional to the frequency, that is what you have studied. But when it comes to diagrammatical representation, so time axis, the time domain signals are represented as the x-axis will be represented with time, the y-axis will be represented as amplitude. Whereas in frequency domain, the x-axis will be represented as frequency and y-axis is represented as amplitude. It is in terms of, or we call it as gain or attenuation. It will be normally in terms of dB. So these are the differences between time domain and frequency domain representation of signals. Okay, so we shall go in detail about the frequency domain analysis in the next chapter. Right now we concentrate more on time domain representation. So the other way of telling it is it's just a characterization of input output behavior of LTI systems. In both the case, what actually we are doing is we supply some input, how your system behaves for that given input and what various kinds of output it will produce at the output. That is what we observe and that is what we call it as characteristics. You know, to understand your friend's character, what you do, you talk to him, or sometimes you become angry, or sometimes you share some secrets, some before you believe or trust on anybody, you give some, you keep some checkpoints, right, to just measure the trust, whether the person is trustworthy or not, right? You decide on the character of a person on the basis of some checkpoints, some inputs that you provide, and what are the outputs you get from it, from that person. By that you decide that okay, this person is like this, the character of this person is like this. Similarly, you analyze a teacher, right? If you ask, silliest question, whether the teacher scolds or not, if you feel that teacher is scolding, you never ask a question. If you feel that teacher is encouraging, you go on asking question, right? You analyze the character of a person by giving some input and by analyzing how he responds, which we call it as output. In the same way, For a system to be analyzed or to understand the character of a system, we provide certain inputs. Okay, and the output that it is producing, on that basis we characterize the system, we understand the behavior of the system. So we have four different representations that are possible in time domain representation. The first one being the impulse response, the second one being linear constant coefficient differential or difference equation, third being block diagram representation, fourth being state variable representation. This is not there for syllabus. Okay, the fourth one, only first three we are concentrating. So impulse response representation has got two divisions, two classification. One is convolution sum and the another is convolution integral. Convolution sum is applied for discrete time signals or systems. Convolution integral is applied for continuous time systems. Up till now in the first chapter, we were calling DTS as discrete time signal, CTS as continuous time signal. Now on, henceforth, throughout the subject, whenever I use the term or the short form called DTS or CTS, abbreviate it as discrete time system or continuous time system. Okay, so integral for continuous, sum for discrete. And in the second representation, differential equation for continuous time systems, difference equations are used for discrete time systems. And for block diagram representation, both for continuous and discrete time, we'll be having direct form 1 as well as direct form 2. So what makes these two representations different in continuous and discrete, we will understand it when we proceed with this particular topic in later stage. Okay, so with this brief idea, we are starting with very first topic of this chapter, that is convolution. So in the convolution, again we have a lot of subtopics. First, we will understand the introduction. We'll go through the convolution sum and integral. I have to write it, integral, convolution integral. Then LTI system properties. LTI stands for linear time invariant. Other than linear time invariant, we have several other properties to be verified. Those are memory, stability, causality, invertibility. Those four properties in addition we will be verifying. So that's why we have taken this topic as LTI system properties. Then system interconnections of LTI system, that's the next topic. Then LTI system properties and impulse response. This is also important topic. Then the step response. These are the 6 subtopics that we are going to study in convolution. That is first representation, impulse response, first representation. Okay. So to proceed with the introduction of the convolution. The convolution of one function, the input signal x of t, with a second function, the impulse response h of t, gives the output y of t. Very simple. Of a linear time invariant systems. I make this statement simple. Just have a look. The convolution means one function, that is input x of t, with second function. What is that second function? H of t, gives the output y of t by a linear time invariant system. That's it. When you give some input with a function called h of t in a linear time invariant system, whatever output it produces, that is y of t. So this process is called as convolution. And it is a discrete continuous time, we call it as convolution integral. If it is discrete time, we call it as convolution sum. That's it. Okay. If the input signal is unit impulse function or delta function, if I give input as Dirac delta function or impulse function, then if I feed this as an input, whatever output I get, so that we call it as h of t. If it is a delta function or impulse function, then h of t is called as impulse response. These terminologies I had already touched upon in the previous chapter. I'm repeating intentionally so that you should remember it. So when your x of t is equal to delta of t, your y of t will be h of t. Remember that. For impulse function, your system output is impulse response. That's it. If unit impulse function has a time shift like delta t minus t naught, if x of t is delta of t minus t naught, and if I pass it on to the system h of t system, the output that is going to produce is h of t minus t naught. Why? So the output is providing the same corresponding shift that is happening at the input. That's why it is called as time invariant system. It is possible only if it is time invariant system. That's why I said it. Okay, so by default in this chapter we are considering LTI systems itself. Okay, so this is a basic introduction. Now we will proceed with convolution sum. It is for discrete time system. Discrete time systems. Okay, we are applying convolution sum. What is convolution sum? The definition goes like this. X of n is a signal as a weighted sum of basis function. Initially you feel a bit difficult to understand it. Please give some time so you will understand it. Time shift version of the unit impulse signal. X of k represents a specific value of the signal x of n at a time. I'll take a diagrammatical explanation for helping you in this. So x of n is represented as summation of x of k delta of n minus k. I hope you remember the fifth property of impulse function. It was like this. X of n delta of n is nothing but, or delta of n was nothing but x of 0 delta of n. X of n delta of n minus n naught is nothing but x of n naught delta of n minus n naught. I hope you remember this. So this is a fifth property of impulse functions that we studied in the previous chapter. Okay, so what the first terms, this first line tells, it is fetching only x of 0 values, x of n value at n equal to 0, only that amplitude value it is fetching. That's why it is called as shifting or sampling property. This is a shifting or sampling property. We are extracting the sample of x of 0. That's it. Here what we are doing, we are extracting the sample at n equal to n naught. If n naught has some value called 1, it is extracting a value of x of 1. If n naught is 2, if it is extracting the value of x of 2. So at every time it is extracting only one sample. And such a sample, if I add it, summation means what? Adding all these things. Adding each samples will get me the original signal itself. For this, I taken help of a diagram in the very next slide. Okay. Till then, you please keep a hold on it. Now, how the output is represented? The output of the LTI system y of n is given by weighted sum of time shifted impulse response, where h of n is impulse response of LTI systems. Weighted sum of time shifted impulse responses. Here it is y of n, x of k, h of n minus k. So we will derive, this is my input, this is my output. So we will do a derivation to get the output from the given input. Okay, so this output y of n is denoted as, or symbolical representation of convolution sum is star x of n star h of n. From here on we don't call it as star, we call it as convolution. So we call it as x of n convolved with h of n is nothing but summation k is equal to minus infinity to plus infinity x of k h of n minus k. This is a formula for convolution sum. These two are formula of convolution sum, and this is a symbolic representation of a, or operator of a convolution sum. Okay, so now we will brief it on this particular equation. I'll take a diagram for explanation of this. This is a graphical example illustration of the representation of x of n as a weighted sum of time shifted impulses. Just have a check. Just have a check here. This is actually 0. Fine. So x of 0 delta of n minus, this is delta, okay, this is delta, these are deltas. This is x of n delta of n plus 2. This is x of n delta of n plus 1. This is x of n delta of n. That's it. N or n minus 0 or n plus 0, whatever. Just n. X of n delta of n minus 1. X of n delta of n minus 2. So just have a check. This is just x of n. This is x of n. We are applying a sampling property of it. Just have a check. This is minus 2. This is minus 1. This is 0. This is 1. This is 2. I want to fetch only this signal. I want to extract only this sample. How to do it? What I do is I take this x of n, I multiply a delta function. What kind of delta function? The delta function should be having a finite value at this place. If I want to have a delta function at this place, I have to shift it by left by 2 times. How to do it? Delta of n plus 2. This is shifting the delta function by 2 times onto the left. So that is what I did. And when you multiply it with x of n, x of delta of n minus n plus 1 will be having the signal like this. This is strength 1. It will be having value like this. When I multiply this signal with this signal, what happens? So it will be having non-zero value only at n equal to minus 2. So this and this multiplies, and whatever amplitude you have, that will come at the output signal. Rest everywhere its amplitude is 0. Hence these all will give you product with 0 will become 0 itself. So it is extracted the sample at t at n is equal to minus 2. This is why it is called as sampling property. Now, if I want to fetch this particular sample, what I have to do? I have to shift the delta function to the left by 1 time. How to do it? Delta of n plus 1, multiply it with x of n. The meaning is I am getting only this sample, or else I can just write it as x of minus 1 delta of n plus 1. That is what the property says. Similarly, if I want to fetch this particular thing, it is x of n into delta of n, or else x of 0. This is x of 0, right? X of 0. Directly I can write it's a constant. This is a constant, 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 like that. Similarly, if I want to fetch at n equal to 1, it is delta of n minus 1 multiplied with x of n will give you x of n, x of 1 delta of n minus 1. X of 2 delta of n minus 2 will result in this particular sample. Okay, I hope it is clear. That's why x of n signal, this is x of n signal is what? I said this is a constant, 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 constant. The other term that I use for constant is weight. Constant or amplitude or weight. All means same, okay? Now you read it. X of n is a weighted means x of minus 1, x of 0, x of 1, x of 2, all those. Weighted sum. I'm adding all these things. Sum. Weighted sum of time shifted impulses. See, delta of n plus 2, delta of n plus 1, delta of n minus 1, delta, all these are time shifted impulses. So if I add all these things, see here, if I add all these things, this preserved at minus 2, this will come at minus 1, this will come at 0, 1 and 2. If I add it, I'll get original signal, original input signal. So that's why x of n can be represented as weighted sum of time shifted impulses. These are weight. I am adding it. That's why we call it as weighted sum of what? Of time shifted. This is time shifted, time shifted, time shifted. What is this? Impulses. Now you come back to the definition. X of n is a signal represented as weighted sum of basis function. What does that basis function means? It's a time shift version of unit samples, unit impulse signal. Okay, please understand the concept. Very important concept it is. Okay, so with this, I write the mathematical function for this as x of n is equal to what? I should add all these things. X of minus 2 delta of n plus 2 plus x of minus 1 delta of n plus 1 plus x of 0 delta of n plus x of 1 delta of n minus 1 plus x of 2 delta of n minus 2. All the time it is very difficult for me to write all these things because there might be a signal which is very long. So that's why in general what we do is summation, because plus is there, summation, I call it as k equal to, I call this constant index like minus 2, minus 1, 0, 1 as k. It might vary from minus infinity to plus infinity, but here it is from minus 2 to plus 2. Let us keep in general x of k. It's k that is varying. K minus 1 here k is equal to minus 1, 0, 1 like that. K is varying. Delta of there is n in general minus 2, 1, 1, 1 plus 1 here 2 is there, minus 2 actually it is. Whatever comes over here, same thing is coming over here. Minus 1, here also minus 1, because in general it is n minus of minus 1. Here 0, here also 0. Here 1, here also 1. Here 2, here also 2. So here k, here also it should be k. This is what is x of n. That is what is written here. This is a function that we had written, mathematical function. Okay, so now we derive convolution sum. So we understood how to write the input. We understood how to write the input. This one we understood now. Now we will derive this one. Y of n. We will derive this. It is summation x of k h of n minus k. We will derive this quickly. So here x of n is input signal. And what about delta of n? Delta of n is impulse sequence or impulse function. We also call it as sequence. Okay, and y of n is output signal. Remember this. These are the denotions we are using. And to represent it, this is a system, this is input, this is output, and system we represent with h of n. Okay, so remember this. Now what we do is, we know that x of n into delta of n, according to property number 5, what we are supposed to do, it is x of 0 delta of n. X of n delta of n minus 1 is written as x of 1 delta of n minus 1. X of n delta of n plus 1 can be written as x of minus 1 delta of n plus 1. So in general, if I want to write in general, if I'm supposed to write, how to write it, x of n delta of n minus k can be written as how, x of k. So whatever here I'm writing it, x of k delta of n minus k. Okay, so where n is time index. Time index normally a natural integer, it's an integer, whereas x of k is specific value or a constant or a weight of what, specific value of x of n at n is equal to k. Okay, so this is how the representation we understood till now. Now we defined x of n as weighted sum of time shifted impulses, right? I'll show it. Weighted sum of time shifted impulses. Weighted sum of time shifted impulses. We wrote x of n as x of minus 2 delta of n plus 2 plus x of minus 1 delta of n plus 1, so and so and so, x of 2 plus delta n minus 2. We could write it in this fashion, right? So same thing, I write the input first. We could write x of n as, from the previous slide, we could write it as summation k is equal to minus infinity to plus infinity x of k delta of n minus k. For your reference, same thing I have written. Same equation I have taken forward here. This I treat it as 1. This is my input. Now this x of n is fed. So here this x of n will be fed to the system. How to write the output? Y of n can be written as h. H is a system operator. Okay, let me write it as h for your understanding. So this as H, this is a system. H, I am supplying what? I am supplying an input. Okay. Now H, substitute from 1, what do you get? Summation, substitute x of n should be substituted with summation minus infinity to plus infinity x of k delta of n minus k. So what do you get? Summation and x of k. These things are constant. I have already said this is the weight. Constant it is. For constant, if you operate on system, it does not have any effect. So that's why I take it out. I take it out. I took it out and then I apply the system operator only to the one which is variable, not a constant. So this gives what? What is the system output when you supply delta function as an input? If I supply delta function as an input, what is the output? I'll go to the again first slide. If you supply delta function as an input, what is your output? Your output is impulse response, h of t minus t naught, h of t here. Here we are supplying delta of n minus k we are supplying. So your output should be h of n minus k. That's it. That's it. So hence y of n is given by delta summation k is equal to minus infinity till plus infinity x of k. So in place of h delta of n minus k, this is the input to the system. So output will be h of n minus k. That's it. That's it. I'll take it in the new slide. So therefore y of n is equal to x of n convolved with h of n. This is how it is written, which is nothing but summation k is equal to minus infinity till plus infinity x of k h of k, because already system input you have given as impulse function, so output you have got it as h of n minus k. So this is how the output is derived. This is what we call it as y of n. Very important. Very important. This we call it as convolution sum. Convolution sum. So if you supply input as impulse, function or sequence, the output that you receive is impulse response. Okay. So now I think you got some clear idea about the convolution sum. So input, how it is represented with a shifting or sampling property, and if I supply that input to the system, how the output is produced. Okay. So with this idea, we will proceed with the problem solving. So here y of n is equal to x of n convolved with h of n is given by summation k equal to minus infinity to plus infinity x of k h of n minus k formula. Steps for convolution computation. This is for the problem solving. What you need to do? First, plot x and h versus k, since the convolution sum is on k. So I have realized you the importance of the k now. Okay. Next, flip h of k around the vertical axis to obtain h of minus k, because here if I make n equal to 0, you will get h of minus k. I go on incrementing n 0, 1, 2, 3. So h of minus k is needed. So h of minus k is a folded version of h of k. Folded version, how to fold it? We should fold around the vertical axis. Okay. If we do these two steps, it is as good as doing summation of x of k h of n minus k. So shift h of n minus k by n to obtain h of n minus k, multiply to obtain x of k and h of n minus k, sum on k to compute, index n should be kept taken in care, and repeat step 3 to 6. This is the steps. Until I take one problem and solve it, it is very difficult for you to follow just to read the steps. I'll take a problem to explain you. First problem. This problem can be solved in at least 3 to 4 different ways. Okay, I am telling you all those 3 to 4 different ways. This is x of n. This is h of n. These two things are given. Okay, so normally in terms of sequence, will also give it as x of n as here. Here it is minus 1. I write it as minus 1, comma. At 0 it is 1's half, that is half, zero point 0.5. And here it is 1, 1. Here it is minus half or minus zero point 0.5. And at 0 you have 0.5. You have to mark it like this. This means at n equal to 0 you have this value. This is x of n. Similarly, if I want to write h of n, how to write it? So at 0 I am having 0.5. Okay, at 1 I am having amplitude 1. This is 1, this is 2. At 2 I am having amplitude minus half. At 3 I am having amplitude half. So this is how the sequence, in terms of sequence, it is written. Okay, I hope it is clear. Diagram to sequence, sequence to diagram. You can easily write it. Okay, so now this is a given question. You need to perform convolution sum. You have to convolve these two things in order to get y of n. Y of n is equal to x of n convolved with h of n. You have to do this process. The equation that we need to use is here. Summation x of k h of n minus k. The steps are here. So I'll solve with the first step, first way of doing it. There is a huge diagram here, so don't worry. So I'll make it very simple for you to understand. Okay. So first you have to apply a sampling property to the input. So what I have to do, this is x of n. I have taken it for your understanding. This is minus 1, this is 0 0.5, this is 1, this is minus 0 0.5. So here it is 0 0.5, this is 1, this is minus 0 0.5, and this is 0 0.5. 1, 2, 3. This is minus 1, this is 1, this is 2. Okay, x-axis and y-axis I have marked it for your understanding. So first what I do is, first I want to extract this sample. If I want to extract this sample, what I have to do? I have to multiply x of n with delta function. Delta function should be shifted to the left by one time. That is what is done here. You can check. Delta function is shifted to the left by one times, and I am multiplying it by x of n. If I multiply it by x of n into delta of n plus 1, according to the property phi, how it can be written? It is written as x of minus 1 delta of n plus 1. Directly it is written as that. Okay, so I have extracted this particular sample. If I want to extract the sample at n equal to 0, how to do it? Multiply by delta of n. That's it. X of n delta of n is x of 0 delta of n. So only this sample is extracted. Similarly, to extract this sample, delta of n minus 1 should be multiplied. To extract this sample, delta of n minus 2 should be multiplied. So I got all the sample signals. So here I got this particular equation, x of n. If I add all these things, I'll get the input. This is the input, same input. Whatever I'm having here, the same input is here. Now this input I'm feeding to the LTI system. Let me call it as H. So output what I get? System is represented by h of n. See, always remember, system is represented by h of n. Remember it. So this is also okay, this is also okay. So I'll brief it more about it in later stage. Okay, this is how system is represented. This is my input. So I am convolving it with system impulse response. So what I get at the output, that is what we need to do. So what we are supposed to do here is x of minus 1, here this signal, take this signal, multiply it with h of n. If I multiply minus 1 of x of n, whatever sample I have extracted, to the h of n, what all things I have got? Minus 1 into 0.5, what I get? Minus 1 into 0.5 will be getting minus 0.5. But you can see that I am not writing it at 0. I am writing it at minus 1. Why? Because it is h of n plus 1. Shift or left shift by one time. So multiply this one with h of n and shift it by one time to the left, because it is h of n plus 1. Because we are operating at k equal to minus 1. Remember that. K equal to minus 1 means shift the multiplication, whatever it results, shift it by left one time. So now, so minus 1 into 1. will result in minus 1. I have to shift it 1 to the left, so it will come at 0. So I'm having here minus 1 into minus 0.5. It is plus 0.5. I'm having plus 0.5. Here it is at 2, but shifted by left 1 times, it will result in 1. At 1 it will come. So whatever I'm having at 3, it will come at 2. Amplitude is 0.5. 0.5 into minus 1 will result in minus 0.5. This is minus 0.5. I am having at 2. So this is the first signal. We call it as y of minus 1. We normally call it as y of minus 1. This is y of 0. This is y of 1. This is y of 2. Similarly, I'll show this one. So x of 0, I am having half. Half should be multiplied with all the h of n values. Half into half is 0.25. Here it is 0.25. 0.25 it is. Half into 1, it is 0.5. Half into minus 0.5, it is minus 2.5. Half into half is just 0.25. No, sorry, I should have called it as 0.25. 0.25. So minus 0.25, sorry, plus 0.25, plus 0.5, minus 0.25, 0.25. I'm not shifting, I'm retaining as it is because there is no shift operator. It is not time shifted. Just k is equal to 0, you can check here. There is no shifting happening. Similarly, this one. What is the value I'm having? 1. Multiply 1 with all the constant weights here. 1 into 0.5, 0.5, 1 into 1, 1, 1 into minus 0.5, minus 0.5, 1 into 0.5, 0.5. Same thing I get, but shifted by one time because it is n minus 1, k is equal to 1 here. Same thing shifted by one time. 0.5 comes at 1, 1 comes at 2, this is 0.5, and 2, whatever 2 at 2 is there, that will come at 3, and whatever at 3 comes at 4, that is here. And similarly, for 2 delta of x of 2, I am having minus 0.5. Multiply minus 0.5 everywhere. Minus 0.5 into 0.5, minus 0.25. So minus 0.25, but shift by 2 times. I am shifting it by 2 times. Similarly, minus 0.5 into 1 will result in minus 0.5. So you have minus 0.5 here. So it is shifted by 2 times and it is written here. Add all these 3 things, 4 things, plus, plus, plus. It will result in your output. You can see here. At minus 1, I am having only minus 0.5, nothing else. I am writing minus 0.5. Okay. At 0, I am having minus 1. Then I am having nothing. Here I am having. Here I am having 0.25. Minus 1 plus 0.25 will result in minus 0.75. That is at 0. And at 1, what I am having? 0.5 plus 0.5, that is 1. 1 plus 0.5, that is 1.5. 1.5, here I am having 1.5. At 2, what I am having? Here it is minus 0.5. Here it is minus 0.25, that is minus 0.75 happened. 1 minus 0.75 is 1 minus 0.75 is 0.25. 0.25 minus 0.25, it goes to 0. So I am having 0. Similarly, I am having the y of n. So y of n, if I want to write it in terms of sequence for better understanding, I'll write it as this is minus 0.5 at when it is at n is equal to minus 1. When n is equal to 0, I am having minus 0.75. This is at n equal to 0. Similarly, at n equal to 1, I am having 1.5, and at 2 I am having 0, and at 3 I am having it is I think it is minus 0.75. It is same matching here, minus 0.75, minus 0.75, and at 4 I am having plus 0.75, and at 5 we are having minus 0.25. So this is a sequence of output what we get from the diagrammatical representation. And let me tell you some alternative ways to solve it. The alternate way of solving the previous problem is, so let us write the given signal x of n as minus 1, 0.5, it is at 0, 1 and minus 0.5. H of n as 0.5, it is at index 0, 1, minus 0.5 and 0.5. So the table should be built like this. K value should be taken like, so if I write its index, it is 1, 2, 3 and 3, 1, 0, 1, 2, 3. If I take its h of minus k, means if I fold it across the y-axis, vertical axis, this 3's index value will be folded and it will be fallen on minus 3. The index will be at minus 3. Hence, we need to start from minus 3. Minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, and you can stop at some point. And then we have to write x of k. Let me change the ink for better visibility. So x of k, I'll be writing here. At 0, I'm having 0.5, and at minus 1, I'm having minus 1. Rest everywhere, I'm having 0 on the left side. On the right side, I'm having 1 at 1. Here I'm having minus 0.5. This is 0, 0. I mark this window where it is having non-zero value. I'm marking this window. So this will be helpful for my further simplifications. So again, I change the ink. So here, so you know that h of n minus k can also be written as h of minus k plus n. So now we go on writing these things in the table. When n is equal to 0, I can just write it as h of minus k. H of minus k means the folded version of h of n, what is given here. The folded version means at 0, I am having 0.5 itself. At 1, whatever I am having, it will come at minus 1. At 2, what I am having, I'll have it at minus 2. At 3, it comes to minus 3. Rest everywhere, fill it with zeros. Similarly, for n is equal to 1, h of minus k plus 1 should be performed. So whenever I write it as plus 1, you should shift it by right, because it is already reflected version. So don't go with the previous session's analysis. Like when I have plus 1, I have to shift it on left. It's not like that. You should shift it on right, because we have already reflected it. Actually, according to precedence rule, first we need to shift it and then we need to reflect it. But here we have reflected it already. Hence, we are just doing the nullifying effect by shifting it onto the right whenever I'm having plus 1 here. Okay, so if I shift it on the right, what happens? This 0.5 will occupy this place. This will be 0, and here it is minus 0.5. This is 1, and this 0.5 goes to here, and 0 comes over here, 0, 0. Similarly, when n is equal to 2, h of minus k plus 2 will result in, take this, shift it one more time onto the right. 0 here, this 0 comes over here, 0.5 comes over here, minus 0.5, and this 1 comes over here, and this 0.5 comes over here. 0, 0. So similarly, n is equal to 3, h of minus k plus 3 will shift it 0, 0, 0. One more time. Take this one, shift one more time. This becomes 0.5, this becomes minus 0.5, this becomes 1, this becomes 0.5 and 0. So n is equal to 4 will result in h of minus k plus 4, 0, 0, 0, 0. This comes over here. this comes over here 0.5, this comes over minus 0.5, and this comes over 1, 0. Similarly, n is equal to 5. You should proceed until in this red window you should have all zeros. Minus k plus 5 will result in 0, 0, 0, 0, 0 here, 0.5 here, minus 0.5 and 1. N is equal to 6 will result in minus k plus 6, 0, 0, 0, 0, 0. This 0 comes over here. See, all became 0. Now we need to stop. When all became 0, now we need to stop because it will result in a 0 value of product. Similarly, when we shifted right, we got all zeros, we stopped it. Similarly, we need to shift left now. Take h of minus k, this one, shift it to the left. So to shift it left, n is equal to minus 1. H of minus k minus 1. Where is h of minus k? Find it. Here, shift it onto the left one times. Shift it onto the left one times. 0.5 goes off, minus 0.5 occupies this place, and 1 occupies this place, and 0.5 occupies here, and rest everywhere 0, 0, 0, 0, 0. So now one more time, if I shift onto the left, what we get? So we get minus 0.5 goes off, 1, here 0.5 comes, here again 0, 0, 0, 0. Stop it, because in the red window I am having all the zeros. So this is how you need to build a table first. So once the table is built, the further things are very simple. So now we start from n equal to minus 1, because here I am having a non-zero value. I need to consider this. I call it as y of whatever value of n I am having, that I'll write it here, y of minus 1. Y of minus 1 means 0.5, take this, move across the column, multiply it with x of k into h of minus k minus 1. That's how it is, x of k into h of minus k minus 1. So I have to multiply whatever comes in this particular window, because if you go over this window, x of k is 0. That's why be yourself in this window. So I'm multiplying only this value, because here everywhere it is 0. 0.5 into minus 1 will result in 0.5 into minus 1 will result in minus 0.5. This is value of y of minus 1. So let me write y of n values here. This is minus 0.5 for n is equal to minus 1. I'll shortly write it here. Okay, so comma. Now I start with y of 0. Y of 0 will result in, so y of 0 has 1 here, 0.5 here, 1 minus 1, 1 into minus 1 is minus 1, 0.5 into 0.5 is plus 0.25, rest everywhere 0 it is. So it will result in minus 0.75. So that is what you need to write, minus 0.75 here. And this is at index 0, so I am marking it here. So y is equal to, when n is equal to 1, y of 1 is given as this one, this one, this one. 3 non-zero values I am having. Minus 0.5 into minus 1 plus 0.5 plus 1 into 0.5 plus 0.5. Then 0.5 into 1 again plus 0.5. It will result in 1.5. So write it. So 1.5. Similarly, for n is equal to 2, I get this value non-zero, non-zero, non-zero. Everywhere it is non-zero. 0.5 into minus 1, minus 0.5. Minus 0.5 into plus 0.5, minus 0.25. 1 into 1, plus 1. 0.5 into minus 0.5, minus 0.25. Minus 0.5, minus 0.25, minus 0.25. Togetherly it will be minus 1. Minus 1 plus 1 will result in 0. Write it as 0. Next, n is equal to 3. H of minus k plus 3 will result in, Here non-zero value, non-zero value, non-zero value. Here 0, no need to go for product. 0.5 into 0.5, 0.5 into 0.5 will result in plus 0.25. Minus 0.5 into 1, minus 0.5. 1 into minus 0.5 will result in minus 0.5. So minus 0.5 minus 0.5 will result in minus 1. Minus 1 plus 0.25 will result in minus 0.75. Minus 0.75. Next, for y of 4, you will get, these are the two non-zero values. 0.5 into 1, 0.5. Minus 0.5 into minus 0.5 plus 0.25 will result in plus 0.75 plus 0.75. Next, y of 5 will result in only non-zero value. 0.5 into minus 0.5 will result in minus 0.25. Minus 0.25. So y of 6 will result in, so everywhere 0, so this will be 0. Here also y of minus 2 will be everywhere 0, so it will be 0. This completes your answer for y of n. And if you match it with the previous values, minus 0.5, minus 0.75, 1.50, it will match with the value that has been written here. Okay, so there is one more way of solving it again. That way I'll show it here. Alternate way number 2. So 3, it's actually third one. So I write x value minus 1, 0.5, 1, minus 0.5. Here is a 0 index. H of n is 0.5, 1, minus 0.5, 0.5. Here's a 0 index. So what you're supposed to do is, it's a quite very simple one, very simple one. First, take this minus 1, multiply it with all of the constants that has been given for h of n. For example, minus 1 into 0.5 is minus 0.5. Minus 1 into 1 is minus 1. Minus 1 into minus 0.5 is plus 0.5. Minus 1 into plus 0.5 is minus 0.5. So the first index is over. Second one, you take this 0.5, multiply it with all these things. 0.5 into 0.5 plus 0.25. 0.5 into 1, 0.5 plus 0.5 into minus 0.5 minus 0.25. Then 0.5 into 0.5 plus 0.25. Done. Okay, next take this one. 1 multiplied with all these things as it is, you write. 1 into 0.5 plus 0.5. 1 into 1 plus 1. 1 into minus 0.5 minus 0.5. 1 into plus 0.5 plus 0.5. Next, last one. Take this one, multiply with all these things. Minus 0.5 into 0.5 minus 0.25. Minus 0.5 into 1 minus 0.5. Minus 0.5 into minus 0.5 plus 0.25. Then minus 0.5 into plus 0.5 minus 0.25. The table is ready for now. I'll change the ink for the last step. Last step is very simple. So you have to mark it like this, diagonally. So I put a dotted mark. Dotted mark. Put a dotted mark diagonally, this fashion. So this diagonal, this diagonal, and the last diagonal. Okay, so now the things are done. This is what is my y of n. First, what do you get? Minus 0.5, comma. Here, what do you get? You have to take a sum of it. Minus 1 plus 0.25. What do you get? Minus 0.75. So for this value itself, I am multiplying 0.5, right? So this becomes 0 index. Fine. Next, third one. 0.5 plus 0.5 plus 0.5 will result in 1.5. Okay. Now this will result in minus here from here minus 0.5 minus 0.25 minus 0.75 plus 1 and minus 0.5. So minus 0.25 minus 0.25 minus 0.5 results in minus 1. Minus 1 plus 1 is 0. Next, plus 0.25 minus 0.5 minus 0.5 will result in minus 1. Minus 1 plus 0.5 is minus 0.75. Okay. Next, plus 0.5 plus 2.5 plus 0.75. Next, there is only one value. So you can cross check with the previous values. It is the same value. So this is index 0, minus 1, 1, 2, 3, 4, 5. So this is the simplest way of doing. So in your examination, you have to use this step this way for only verification. Okay. And which one is the actual answer that you have to prefer is this one. This is what you need to prefer, or else this one. Alternative one, answer 1 or answer 2. This should be your the answers in your exam. This is for verification. So this completes the problem number 1. I have shown 3 alternatives. Again, you have few more alternative ways. I don't want to confuse you people by showing a lot of alternative ways. So one for verification, 2 different alternate ways for computing your answers. So this completes your the problem number 1 on convolution sum. Thank you. We'll see you in the next session.